AQA GCSE Combined Science Physics Topic 4, which is on atomic structure. So this first task in the pack is for you to write down everything that you know before you start this course. Some of the things you know could be correct, some of the things you know might be incorrect, so you need to pay attention to that. And as you go through the lessons, you can add to this circle map with the things that you discover. Now, at the bottom of the page are some of the basic facts that you need to know. What we're talking about here is one of the theories of modern science. A theory is something that is a scientific explanation of the nature or the way that the universe works. So a theory has to explain it. So it has to be, this is happening because, and then the theory will allow us to answer that part of the question, why, or the part that's because. And a theory is also something, as well as being an explanation, is somewhere where the overwhelming evidence of all observations and scientific experiments show us that this explanation matches the way that the world behaves. So it can be changed. Sometime in the future, people find a new explanation for the way the world works that explains some results of experiments that aren't explained by a theory that we have. Then we replace the old theory with the new one if the old one doesn't explain how the world works. Now, the atomic theory is one of those theories that is overwhelmingly supported by the evidence from experiments and the world around us, and it explains pretty much most of the things that we see in science, in physics, chemistry and biology. We can put that back to the way that atoms behave, how they interact, will explain most of the phenomena that we see in the world around us. So what is the atomic theory? The atomic theory is an explanation that says everything that we see, that's objects, material, the substances that we see around us, are made up of tiny small units, discrete units that are called atoms. We can't see them because they're very small, with the radius of an atom being around about 10 to the power of minus 10 meters. That's incredibly small. And the task you need to do here is try and calculate how many atoms could we fit into this 1 litre bottle. How many atoms would there be if we filled that to the top? So we said that the volume of the bottle is 0.001 meters cubed. We assume this atom is a sphere, that's a ball, and the volume of a sphere is 4/3 pi r cubed. Now I'm going to ignore the 4/3 pi parts and just say it's roughly equal to the radius cubed. So the volume of one atom is going to be around about 10 to the power of minus 10 meters cubed. So that's 10 to the minus 30 meters cubed. So the number of atoms in 1 litre bottle is going to be 0.001 meters cubed divided by 10 to the minus 30 meters cubed, which is 10 to the 27 atoms. So that's 1, 2, 3, 4, 5, 6, 7, 10, 11, 12, 13, 14, 15, 16, 17, 19, 20, 21, 22, 23, 24, 25, 26, 27. That number of atoms, which I think you agree, is a very, very large number. So that's how small atoms are. There are this number of atoms inside a 1 litre bottle. Notice, by the way, that I've done my calculation with the calculator. That's just to remind you that in physics, we can always use a calculator. We don't have to do any calculations with mental arithmetic. Now, in this next part, you had to fill in the table using the information that's in the PowerPoint. And there are also 2 more facts to remember, which are really important. We had the fact from the previous page, which was that the atom, the radius of the atom is about 10 to the minus 10 meters, which is very small. However, we also should know that most of the atom is actually in empty space, and most of the mass of the atom and all its positive charge is in the nucleus, which is 10,000 times smaller than the atom. So the atom is already incredibly small, and the nucleus is 10,000 times smaller than that. So using the PowerPoint, we need to fill in this table. So here we have all the information about what the atom is made from. It's made from 3 things. First thing is called a proton. A proton, it's got a mass of 1. We say it's a relative mass, so it's its mass compared to a proton, so its relative mass is 1. And it's got a charge of +1. The neutron, it also has the same mass as the proton, but its charge is 0. And the electron, which is a very tiny particle, it's got a mass that's 1 over 2,000 times smaller than that of the proton, but it's got a charge of -1. And then when we see where these are inside the atom, we see that the protons and the neutrons, which is pretty much most of the mass, because these are the large particles, they're inside this nucleus in the center. So all the positive charge and most of the mass is in the center, in what we call the nucleus. And the electrons are in these things that are called shells, particularly by chemists. Physics, we tend to call them energy levels, which we'll see why later. And they could sometimes also called orbits. So this circle is meant to show that the electrons, they're not inside the nucleus, they're outside the nucleus in this sort of distance away from the nucleus. There isn't actually physically a circle or a membrane around the atom. This is just showing that the electrons are found particular distance away from the nucleus, and we call that the shell. The diagram is a little bit misleading because it shows the nucleus as being quite large compared to the atom. Remember, the nucleus is 10,000 times smaller than the atom. That means that here's our atom. The nucleus, in fact, would be a dot that's so small that we wouldn't be able to see it. So this is closer to what the atom looks like. But we draw it like this so that we're able to see there are the protons and the neutrons, so we can label it. Now we'll think about the atoms themselves. So the first thing we can say about atoms is, and remember we've said that the atomic theory is saying that everything, all matter, is made up of these little things called atoms. So the first thing we can say is that if we've got an element, so that's a particular substance that appears in the periodic table, like iron or hydrogen, then all the atoms in an element are the same. They're the same type of atom, and they are different to the atoms that are in all the other elements. So in other words, the atom of hydrogen is the same atom in hydrogen, so all the atoms of hydrogen are exactly the same, but they are different to the atom of, let's say, oxygen. So all the atoms in oxygen are exactly the same, but they are different from the atoms of hydrogen. Now there are 3 particles that we saw in the atom, the proton, the neutron, and the electron. So how the atoms different, because all the atoms of hydrogen and the atoms of oxygen and the atoms of iron, are all made from the same 3 particles, protons, neutrons, and electrons, so that the way that the atoms of elements differ, so the way that the hydrogen atom is different from the oxygen atom, is in the number of protons. So that's the only way that these atoms are different. And the way that chemists have represented this is they have something called the periodic table. And the periodic table has got a number in it that tells us the number of protons, and it's called the atomic number, and it's shown here. So whenever you look at a periodic table, you'll see that there is a symbol for a particular element. So we've got lots of these little boxes in the periodic table, and this is the symbol for the element. And we've got 2 numbers, a small number, usually at the bottom, and a larger number. And the small number is the number of protons that are inside the atoms of that element. It's called the atomic number. In this case for lithium it's 3, so it's telling us that lithium has got 3 protons. The mass number is telling us how many protons and neutrons there are altogether inside the nucleus. So in this case for lithium, the number of protons and neutrons added together is 7. So when you look at a periodic table, which looks like this, you can see you've got all these little squares. Each of these squares have got 1 element in it. For example, here's our element lithium, and it's got the atomic number, which is telling us all the atoms of lithium have all got 3 protons, whereas this one, Be, is beryllium, and all the atoms of beryllium are different to those of lithium because they've got 4 protons. Okay. So the difference between the atoms of different elements is the number of protons. So all the atoms of the same element, all the lithium atoms, have all got the same number of protons. In the case of lithium, that's 3. So what you need to do is we have a periodic table, and we're going to use that periodic table to complete this table where we have to find the elements. So we're going to use the periodic table to help us. We find the elements, we write down its symbol, its atomic number, the relative atomic mass, and we're going to round this number because we'll find that in the periodic table the mass number is often written to a number of decimal places, so we'll need to round it. That way we can write down the number of protons, the number of neutrons, and the number of electrons. So if you complete that now. So here we have the completed answer. So we see magnesium, its symbol is Mg. It's got an atomic number of 12, so that is the number of protons. So by just looking at the atomic number, we write that as the number of protons. The atomic mass, that's the bigger number that's in the table. So the smaller number for magnesium is 12, that's the atomic number, the number of protons. The larger number, that's the mass number. It's 24.3, which we round down to 24, and that gives us the number of neutrons is 12. 24 minus 12 to equal 12. And we do that all the way through. So we find, for example, for the gold, its atomic number is 79, so it has 79 protons. Its mass number 197, so it's got 118 neutrons, which means it's a very, very large atom when you compare it to the magnesium. The number of electrons are equal to the number of protons. So whatever number we have for the number of protons, that's the same as the number of electrons. So what you need to do now is when you turn the page, you'll find you have this question to answer. Why is the number of electrons equal to the number of protons? And what you should think about is the charge on an electron, the charge on a proton, and the charge on an atom. So make an attempt to answer that question now. Okay, and I want you to pay particular attention to how I've written this in case this ever came up in an exam, and we'll see how we answer this sort of question. It's very important when you answer a question like this that you explain your answer fully. You don't leave any part unexplained. So it says, I started by saying atoms are neutral. So that's the first thing we can say. And what does that mean that they're neutral? It means that the overall charge of an atom is 0. It doesn't mean that atoms don't have a charge inside them. It just means that overall the charge is 0. Now we know that the electron has a charge of -1 and the proton has a charge of +1. So for that overall to be 0, there must be the same number of electrons as protons, so the overall charge cancels out to give us 0. So in terms of answering this question and explaining it fully, you have to include those elements. You have to say that overall the atom is neutral, that is, its charge is 0. But the electrons have a charge of -1 and the protons have a charge of +1, which means that they must be the same number of electrons as protons, so the overall charge cancels out. So in answering this question, we have to give all of that information for it to make sense. Okay, so here's a little practice question using the information that we've already looked at for you to attempt. Okay, so the first part we had to fill in, label the different things on the diagram. So the ones that are not inside the nucleus are the easiest to identify. Those are the electrons, which are these black circles. And the thing to notice there is that we have 3 of them. Okay, this is meant to represent an atom, which means it must be neutral. So the number of electrons has to be equal to the number of protons. So when we look inside the nucleus, we've got 3 of the shaded circles, and then we've got 4 that are not shaded. So that means that these ones here must be the protons, because there are 3 of those, which equals the number of electrons, and we have 4 of the other ones, which are our neutrons. Which type of particle inside the atom is uncharged? That's very straightforward, that's the neutron. What is the mass number of this atom? Well, the mass number, we add together the number of protons and the number of neutrons, so we get 3 protons and 4 neutrons, so our answer is 7. Why have we said that? Because the mass number is the number of protons and neutrons in the nucleus. So far we've talked about the periodic table, and we've shown that all the atoms inside an element are all the same. They have the same number of protons, and the mass number in the periodic table is made from the number of protons plus the number of neutrons. We haven't really spoken about the electrons. apart from saying that the number of electrons is the same as the number of protons because the atom is neutral. So how do we know that the electrons are in these shells, or we call them energy levels in physics? Where does that idea come from? And it was a scientist called Niels Bohr who came up with this idea of the electrons that are in energy levels or shells. And this was used to explain something about the way that materials behave when they are heated. So whenever we heat something like a metal, first of all, it will start to, when the temperature gets high enough, it will start to glow red hot. And if we increase the temperature further, it will eventually start to glow white hot as the temperature goes even higher. But the metal is glowing, and the thing that Bohr did by putting the electrons into these energy levels, he was able to explain why the metals glow. So I want you to look at the parts of the PowerPoint related to the electrons and the energy levels, and then answer these two questions. Describe how an electron can move between energy levels, and then what is created when an atom gains or loses electrons. So the electrons are in these energy levels or shells, but the electrons can actually move between the shells. So the way that they can move to a higher energy level is when they absorb electromagnetic radiation. And the thing to realize is that the higher energy levels are those shells that are further away from the nucleus. And it works like this. So I have a pen sitting on the desk here. The pen is staying on the desk. It's not flying up into the air because it is being pulled down by gravity. And in this case, the thing that's pulling it down is the Earth. So the Earth is pulling this down with a force that we call gravity. The nucleus has got a positive charge, so it's pulling the electrons down with the electrostatic attraction between the electron and the protons. They have opposite charges, so they attract. So it's a very similar situation to the pen that's on my desk. The pen is being pulled downwards by the Earth, by gravity. Inside the atom, the electrons are being pulled downwards by the nucleus. Now, if I want to move the pen upwards, what I need to do is I need to use some force from my hand lifting the pen up, which causes a transfer of chemical energy to gravitational potential energy. My pen has now got higher gravitational potential energy. And the higher I lift it, the more gravitational potential energy I give it. So in the same way, when the electron is moved upwards, it increases its energy in the same way that the pen increased its gravitational potential energy. The electron increases its energy as it moves away from the nucleus. Now, in the case of an electron in an atom, that can't be done by someone grabbing hold of the electron and moving it up. It's much too small. So instead of, as in the case of the pen, it's my hand that's causing the pen to move. The way that the electron is moved is through it absorbing electromagnetic radiation. So it absorbs electromagnetic radiation. That causes it to move to a higher energy level. When it falls back down, it releases that energy. So here I have the pen. It's at a higher energy level. When it falls, we can hear the energy has been released as sound energy in this case. When the electrons move down to a lower energy level, they release the energy as electromagnetic radiation, which can include visible light. So that can cause things like metals to glow. So the reason why Niels Bohr added this to the idea of the nuclear model was because it explained things that we see in the world. It explained why it is that metals glow when we heat them, because the electrons have been moved to a higher energy level by absorbing electromagnetic radiation, infrared radiation, for example, from the heat, and then they fall back down and they release electromagnetic radiation as visible light. Now, the next thing we should ask is what happens, or what is created when the atom gains or loses electrons entirely. So in this first case, the electrons they're still attached to the atom. They're just moving between the energy levels. But what would happen if we added an entirely new electron into the atom, or one of our electrons got so much energy it left the atom entirely? So it's completely gone. So it's not gone to a higher energy level, it's completely gone. What do we get created when an atom gains or loses an electron? So in physics, we're mostly interested in when atoms lose electrons. In chemistry, you can have cases where atoms can gain as well as lose electrons in chemical reactions. So if an atom gains so much energy from radiation that an electron can escape, so the energy, it's got so much energy it didn't get up to here or up to here, it left entirely, then we say that the atom has been ionized. That just simply means the atom has become an ion, and this is a word that you'll be familiar with from your chemistry. The radiation that causes this to happen is called ionizing radiation. Now, in the first task, you were looking at how we developed our ideas of what's inside the atom and how it behaves. Over 2,000 years ago, there was a philosopher who suggested that matter was made up of tiny indivisible particles. His idea wasn't based on any experimentation. It wasn't based on the scientific method that we use nowadays. It was simply based on looking at material like sand, because he knew that sand came from the process of water grinding down pebbles and stones, smaller and smaller until they became sand grains. So he thought that perhaps this is what everything is made up of, tiny little round solid objects like sand grains, and he called these atoms. Now, his idea was that's as far as you could go. There were these little small round balls that everything was made from, and those couldn't be split up because they were indivisible. Now, name one discovery that led to changes in our understanding. Well, it can be, for example, the electron, the proton, or the neutron. Once we discovered that the atom was actually made up of things, that meant it was no longer indivisible. It was actually made up of separate little particles, and particularly with the electrons, these particles can be taken away or added to atoms so it's no longer indivisible. So this meant that his idea had to change. So this lesson is all about how we developed the model of the atom. Now, the model is how we explain something in the world or the universe. It allows us to be able to not just describe what we see around us, but to say that something behaves in this way because, and we have a reason to explain why it behaves like that. It also allows us to make then predictions about what will happen then when we use this material or do something else. So it has to be able to explain two things, and I'm going to say this in terms of the atom. It should explain what the atom is made from, its composition. So it should explain what the atom is made from, and it should explain how it behaves. What changes might we see? So we should be able to explain what it's made from and how it behaves. And we based our model, our idea about how this behaves and what it's made from, on observations of the world around us. So for example, we observe that atoms are neutral. How do we know this? Because material just doesn't randomly attract and repel for a hidden reason, because the atoms, we can't see them. We know that we don't see those effects, so the atoms are neutral. So we've got the observations of how the world behaves, and then we've got experimentation, where scientists say, well, if the model is true, then when I do this, I should see this effect, and we can do experiments to test that idea. So because this is what a model has to do, as new discoveries were made, which meant we had to change what we thought the atom was made from, which is what happened with Democritus's idea. As we discovered new ways in which atoms behave, we have to change our model. So the model of the atom changed as new discoveries were made about what it was made from and how it behaves. So in this section, you need to make a flow map to describe the development of the atomic model. You can use the video and the PowerPoint to help you do this. and you should show the main steps in development of our model of the atom, starting with Democritus, then John Dalton, J.J. Thomson, Ernest Rutherford and his experiment, Niels Bohr and the energy levels, and then finally James Chadwick, how each of these people contributed to developing our modern model and understanding of the atom. So here we have the development of our modern understanding, our modern model of the atom, the nuclear model. We start with Democritus in 400 BC, and he had this idea about everything being made of tiny, indivisible, indestructible particles. He wasn't able to say how many types of these particles would there be. Would each substance have its own type of particle, or was there a single type of particle that was made, everything was made from? Because this was not based on any scientific evidence or any evidence based from experiment. It was just a thought experiment from this philosopher based on thinking about material like sand. And because there was no evidence behind this, he wasn't able to show that he could predict how things behave because of this idea of what matter was made from. So people for many thousands of years held to the Aristotelian idea, which was that things were made up of different mixtures of what Aristotle called the elements air, water, earth and fire, which is clearly wrong. But neither of those ideas had any scientific evidence underlying them. So it was only in 1803 that we had the first real scientific development of a model of atoms. So John Dalton, he came up with 4 ideas in his atomic theory. All matter is composed of atoms, and atoms cannot be created or destroyed, so this is the same as Democritus. But then he added these ideas that all atoms of the same element are identical, and chemical reactions are the rearrangement of these atoms, and compounds are made from 2 or more atoms. So this disproved Democritus's model, which was replaced by Dalton's model. And the evidence for this is essentially that Dalton's model could explain all of chemistry and predict what would happen with chemical reactions. Then 1897, so sometime later, but still a lot shorter period of time than between Democritus and Dalton, J.J. Thomson, a physicist in the UK, discovered the electron. He discovered a negatively charged part of the atom that could be separated out from the atom using something called a cathode ray tube, which is what televisions used to be made from. And this allowed him to develop his idea of what was called the plum pudding model that we'll look at in a bit more detail. So his evidence was he was actually able to discover the atom wasn't indivisible. There was a negatively charged part of this atom called an electron. So it disproved Dalton's model. However, he kept all these parts of Dalton's model were kept and incorporated into his model, which was called the plum pudding model. So his model explained why there was this negatively charged thing called the electron, but it also was still able to explain all the things that Dalton's model could explain in terms of chemistry. Then a few years later, Ernest Rutherford did an experiment called the alpha scattering experiment, which disproved the plum pudding model. So his model said that all the mass and positive charge were in the center of the atom, which was mostly empty space apart from some electrons that were outside this area in the center. And again, his new model, it was incorporating all of Thomson's and Dalton's ideas, but it disproved the plum pudding model. Now, there were problems with his models which were solved by Niels Bohr in a couple of years later, who came up with the idea of the electrons being in these discrete energy levels or shells. And the evidence for this was the movement of these electrons that we discussed before between the energy levels. So Bohr, in his nuclear model, was able to explain these observations, as well as everything that was included in Thomson's model and Dalton's model before. And then finally, in 1932, sometime later, the neutron was hard to discover because it's not charged, whereas the electron was easier to discover because it's charged, so it's attracted to things that are positively charged. It took quite a time later before the neutron was discovered, but that finally gave us the complete nuclear model explaining everything we know about the atoms, that we can see the elements in the periodic table as it explained the mass number of the atoms with the discovery of the neutron in the nucleus. Now in this next task, what you need to do is, using the video and the information on the PowerPoint, you need to describe the alpha particle scattering experiment. What was the hypothesis, how was it done, what results were found, and what conclusions were drawn from that these results to this experiment. And the point about the alpha particle scattering experiment, which is a very important part of this topic in terms of any exam questions, is, remember, the point of this alpha particle scattering experiment, this gave the evidence that disproved the plum pudding model. So it shows us this process of how the model, a new model is developed that explains more things. It explains things that the previous model couldn't explain. So the previous model is disproved and we go with the new model. The new model isn't proved, so Dalton's model was used because Democritus' model was disproved. But then Dalton's model was replaced with the plum pudding model because Dalton's model didn't have any electrons in it. So each model is replaced when something is discovered that it can't explain. And the alpha scattering experiment disproved the plum pudding model. So here you need to complete this page using the PowerPoint and the video resources to help you. So as with all experiments, we start with the hypothesis. The hypothesis here was the plum pudding model, the model proposed by J.J. Thomson. And this model said that the mass and positive charge are distributed throughout the atom, and there are these small negatively charged electrons embedded inside. Now, from this hypothesis, it predicted that the alpha particles, which we'll talk about in a moment, they would pass straight through the gold foil if the plum pudding model is true. There might be a slight deviation, so some of the particles might go slightly off to the side, but essentially that they would pass straight through. So what did they do? They fired these alpha particles at high speed at thin gold foil. Now, alpha particles are large, positively charged particles. We're firing them at very high speed at very thin gold foil. Gold is used because it can be made very, very thin. So it was expected it would just go straight through the gold foil. Now, what results did they find? They found that, yes, indeed, most of the alpha particles did go straight through with some deflection. A small number of these particles were deflected, but a few of them were deflected by very large angles, even deflecting backwards, and this was completely unexpected. So what did this mean? Well, this result, that a few of the alpha particles were deflected backwards, is not predicted by the plum pudding model hypothesis. So because the results did not match the predictions from the plum pudding model, it meant that the plum pudding model is definitely wrong. It was disproved. Be careful to realize this does not mean that this experiment proves the nuclear model. It just disproves the previous model, the plum pudding model, because that was the hypothesis. The results don't match this hypothesis, so the hypothesis, the plum pudding model, is wrong. So they had to come up with a new idea for a new model that incorporated all the ideas from Dalton and from Thomson, but would explain these new findings. So this is what they proposed. They proposed that most of the atom is empty space, and that most of the mass and the positive charge is concentrated in a very small space in the middle. How did they ensure that the results were valid? Well, they repeated the experiment 100,000 times. So what you now need to do is a double bubble map to compare the plum pudding model, which has been disproved, with this new model, the nuclear model, which was developed in response to this experiment. So let's compare the plum pudding model and the nuclear model. Remember, this is the one that was disproved by the alpha scattering experiments, which meant that we needed to develop a new model, which is now called the nuclear model. So there are some things that are the same. Both the plum pudding model and the nuclear model say that all matter is made from atoms. Both of these models follow all the rules from Dalton's model. that the elements have the same type of atom, and chemical reactions come from the rearrangement of atoms. And they both say that the atoms are overall, they are neutral. And they, most importantly, both have the idea of electrons are incorporated into the model. So both of these models can explain the electrons, which Dalton's model couldn't. However, the plum pudding model had some particular things to do only with the plum pudding model. It suggested that the mass and positive charge were distributed throughout the atom, so there was no empty space, and that electrons were embedded in the positive charge. And we saw that this was disproved, and the nuclear model, which could explain Rutherford's experiment, is mostly empty space, whereas the plum pudding model with no empty space, that most of the mass and all of the positive charge are concentrated in a small space called the nucleus, whereas in the plum pudding model, the mass and positive charge are distributed throughout the atom. And finally, in the nuclear model, the electrons are in energy levels not embedded into the positive charge. So those are the similarities and the differences between the plum pudding model and the nuclear model. So in this last lesson, we're looking at isotopes and radiation. And the first thing you need to do is we've got 3 pictures, sketches of the nuclear model of 3 atoms. And you need to say what are the similarities and differences between the images in terms of the subatomic particles. So we have image A, which has got 1 red circle in the center and 1 small green circle in this energy level. B has still got 1 small green circle in an energy level. It's now got 2 circles in the center, 1 red and 1 blue. And then finally C has got, again, 1 small green circle in the energy level, 1 red circle in the center and 2 blue ones. Well, we know that the number of electrons equals the number of protons if each of these are atoms. So that means we've got, this is the proton, this is the neutron, and this is the electron. So what can we say? So similarities. So all the atoms have 1 proton and 1 neutron. 1 electron, beg your pardon, 1 electron. So all the atoms have got 1 proton, which is one of the red ones, and 1 electron. And the difference is A has no neutrons, B has 1 neutron, and C has 2 neutrons. So the difference are in the number of neutrons. The number of proton is always the same, it's always 1 proton, and the number of electrons is always the same, it's always 1 electron. So next you needed to suggest which element is shown in the diagrams and why are there 3 versions. Well, what we have in this diagram is we always have, these atoms always have 1 proton, and remember that it is the number of protons that tell us what the element is. So all of these atoms have got 1 proton, which means they're all from the same element, and the element with 1 proton, an atomic number of 1, is hydrogen. So what can we say? Which element is this? This is hydrogen, as all the atoms have 1 proton, which is the atomic number of hydrogen is 1. Why are there 3 versions? There are 3 versions because the number of neutrons changes. So we'll note that even though we change the number of neutrons from 0 to 1 to 2, it's always still the same element. It's always atoms of hydrogen. So these are called isotopes, and nearly all elements in the periodic table have got these things called isotopes. So here I've redrawn the picture that we had before, and we've got these three atoms. Each of these atoms has got one proton, which means these are all atoms of hydrogen, but their number of neutrons is different, 0, 1 and 2. So this is what hydrogen atom looks like. So most hydrogen has atoms that look like this. So nearly, it would say 99.98% of all hydrogens are this type of hydrogen. Hydrogens that have got an extra neutron, they've got one neutron, which means their mass number is now 2 because they've got a proton and a neutron. These are known as deuterium. And if there are 2 neutrons, which gives a mass number of 3, it's known as tritium. So these are isotopes of hydrogen. So this question, what is an isotope, is a really common question in an exam, and it's really easy to get wrong. So there are a few things that you need, 3 things you need to say. First of all, isotopes are atoms. They are atoms. That's what an isotope is. It's a type of atom. And they are atoms with the same number of protons. That is the same atomic number. So there are atoms of the same element, but different number of neutrons. So they have a different mass number in their nuclei. So they have the same number of protons, different numbers of neutrons. Isotopes are atoms with the same number of protons, different number of neutrons. So these are isotopes, all isotopes of hydrogen. So here we have to label the diagrams for carbon isotopes. So here I've got 2 isotopes of carbon, and these isotopes are called carbon-12 and carbon-13. And we can find this out by counting how many protons and neutrons we've got. So here we've got 1, 2, 3, 4, 5, so we've got 6 protons, and we've got 1, 2, 3, 4, 5, 6 neutrons. So this is the mass number, and this is how we describe isotopes. Carbon-12. It's an isotope of carbon that has got a mass number of 12, 6 protons and 6 neutrons. Here in this one, carbon-13, so this is the mass number is now 13. We see we've still got 1, 2, 3, 4, 5, 6 protons because it's the same element carbon, but now we've got 1, 2, 3, 4, 5, 6, 7 neutrons to give us a mass number of 13. Now a quick practice question, and here we told the diagram shows 2 isotopes of oxygen. Use the information from the diagram to describe 2 ways in which these show that the atoms are of the same element. Okay, there's a typo there that should say the atomic mass is 16. Okay, so use the information from the diagram to show 2 ways that this shows that these must be atoms of the same element. Well, one way is that they have the same number of protons. So in both cases we have 8 protons, so this must be this atoms of the same element because it's got the same number of protons. The second reason is very much simpler, and that's because they've got the same name and the same symbol. It's written oxygen. So the diagram is telling us these are the same from the name here and from the symbol. Explain why these 2 atoms are called isotopes. So isotopes are atoms, and again note that I've started by reminding us that these are atoms of the same element, which these are, with the same number of protons but different number of neutrons, which is the case here. Here, the first atom has 8 neutrons, the second has got 10. neutrons. So these are atoms of the same element, the same number of protons, but they have different number of neutrons. Now, the next idea is sometimes a little bit tricky to think about, so we just want to give this a moment to think about this. Some isotopes are stable, that is, they do not change. Now, you can think of this like this box. If I put this box on my desk and I go away for an hour and I come back, I'm expecting that just to be still sitting there. If it's moved or it's changed or if it's not there anymore, I would say, well, who came and moved this? Did somebody pick this up? I would expect that something has happened externally to this box to cause it to move. Somebody had to come along and pick it up and move it around or take it away. Okay, it's stable. On its own, it will not change. Okay. However, if I was to try and stand this up like this and leave it alone, it's going to change. It starts in this orientation, but it will change. I didn't cause it to change there. It changed itself. It was unstable. Okay, it means it will change easily. So in the case of this box, this is an example of where it's stable. This is an example of where it's unstable. And the same thing applies to isotopes. Now remember, isotopes are atoms of an element, and some of them are stable. They do not change. So they're just going to, for example, this one might be stable. It's got 8 protons, 8 neutrons. It has its electrons. Unless there's a chemical reaction, it's just going to remain like that. Others are unstable. That means they are going to change easily. So perhaps this one might change, and it might, for example, lose some of its neutrons, or maybe some of its protons would change. Something's going to happen to change this one if it's unstable. So I had my example of an object either standing up, being unstable, lying flat, being stable. You complete the map showing your examples of some things that are stable, the bridge map with some things that are stable or unstable. So let's just make sure we can fill this out and get a proper definition for what a stable and unstable isotope is. So the nucleus of an unstable isotope, remember the unstable isotope is going to change. Well, how does it change? It changes by giving out radiation to change it from something that's unstable to something that's stable. So this is the same as this object. To become stable, it falls over. The isotope, to become stable, if it's unstable, it gives out radiation. We call this radioactive decay. It's a random process. That means it's impossible to predict when this is going to happen. We can, however, say how often it happens. So activity is the rate at which a source of unstable nuclei, if I've got a big bunch of these unstable isotopes, I can tell how many of them are going to change in every second, but I can't say when one particular one is going to change. It's a completely random process. So the task here is to label the diagram to show what happens with the nucleus inside an unstable isotope. So the nucleus inside the unstable isotope is called an excited nucleus. So this is in the unstable isotope. So this is the nucleus of that atom, the unstable isotope. And this becomes a more stable nucleus. And remember, that means when it's unstable, it changes, and it changes to one that is stable. But it also gives out some energy, shown by this yellow, and these things, which are particles. So we've got the nucleus of an unstable isotope becomes the nucleus of stable isotope plus energy and or particles. Now we can measure the activity of the radioactive isotope, that is how quickly radioactive or unstable nuclei are changing. And we measure the activity using something which is called a Geiger Muller counter, or a Geiger Muller tube. Now, it's measured by counting the number of decays per second. And remember, when we say a decay is a change in the nucleus. That's what a decay is. What units is it measured in? It's measured in units of becquerels. That's shown with the symbol capital B, small q, and 1 becquerel is equal to 1 decay every second. Okay, so what we've got is an unstable isotope. It's radioactive. That means it can change through radioactive decay, which is a random process. And when it decays, when it changes, it gives out some form of radiation. Now, there's 4 types of radiation that we need to know about. We need to know about alpha particles that could be given out when it changes, beta particles, neutrons, or energy in the form of gamma rays, which are a form of electromagnetic radiation. And all of these things are coming from the nucleus. So when there is this change on the unstable isotope, from the nucleus we get out either some particles or some energy. Particles could be alpha, beta, or neutron, alpha, beta particles or neutrons, and the energy is in the form of gamma rays. Now we've got this table to complete. So we've got the 3 main forms of radiation, alpha, beta, and gamma. You don't need to fill in any information about the neutrons, just that it could happen. Each of these has got a particular symbol. So the symbol for the alpha particles is this symbol here, which is the letter alpha from the Greek alphabet. For beta, it's shown with the beta symbol, and for gamma, this is the symbol for the gamma rays, or the gamma electromagnetic radiation. So using the PowerPoint, you need to complete this table. So one of the important things to realize when you correct this table is that the answers I'm going to show you here, these have come directly from the revision guide. And again, it's to emphasize to you the importance of using your revision guide in a clever way. In the revision guide, they've got certain words and phrases that are often in different colored font. They're shown in bold font, and they're often underlined as well, maybe even in larger font. And that's done to just indicate to you that these terms are important. They often, in fact, appear in the mark schemes for questions. So just recall that the use of these particular words is chosen particularly because it's what's most likely going to appear in the mark scheme for questions. So alpha particles, they're very large, heavy particles. They're made up of 2 protons and 2 neutrons. So overall, they've got a mass of 4. Their charge is +2 because we have 2 protons. They're what's called strongly ionizing, and we'll look at what that means in a moment. They can't travel very far. They can only travel a few centimeters in air, and they're stopped simply by paper or even by skin. So they're not able to get through even a sheet of paper or through your skin. The beta particles, they're very small. It's 1 electron. So a beta particle is an electron. So the mass is very small. It's the mass of an electron, which is 0.0005 compared to the mass of the alpha particle, which is 8,000 times larger. But they have a charge of -1. They are moderately ionizing. They can travel a few meters in air, and they can be stopped by a sheet of aluminium. And then we have the gamma radiation. And the gamma radiation, this is an electromagnetic radiation, so it's a gamma wave. It's not a particle, it's a wave. And so hence it has a mass, which is 0, and it has a charge of 0, and it's weakly ionizing. How far does it travel in air? The gamma radiation can travel very long distances in air, and to stop it you either need a thick sheet of lead or meters of concrete. Remember, all of this, these are the types of radiation coming from the nucleus when we have radioactive decay. So it's the nucleus of an unstable isotope when it undergoes radioactive decay. Now the ionizing, remember the ionizing, we met this word before earlier in the pack, and it was about what happens when an atom loses an electron. And we said all the way back on page 8, if an atom gets so much energy, then it's said to be ionized when an electron escapes. It becomes an ion. So that means that alpha radiation will remove electrons very easily from atoms. Okay, and this is what makes it dangerous, because it can change atoms to become ions, and ions mean there can be chemical reactions. It can change molecules. So alpha is strongly ionizing. It will remove electrons from atoms. The beta is moderately ionizing, so it also will remove electrons from atoms. And the reason for that is the alpha has got a plus charge, so it attracts electrons away from atoms. The beta has a minus charge, so it repels electrons off atoms. But then we can see the gamma radiation, that will only ionize atoms if there's a direct hit between the gamma wave and the atom in the material. So it is weakly ionizing. However, the alpha can only travel a few centimeters, whereas the gamma can travel long distances. So what that means is we can say that the alpha, this is the most dangerous type of radiation. Why? Because it's strongly ionizing. However, it's only the most dangerous type of radiation when the source is close, because it can only travel a few centimeters in air. So if we're worried about radiation, if the source is very close to us, then alpha was the most dangerous. Gamma is the most dangerous far away, because it's the only one that can travel long distances, and it is the least dangerous when close. And beta radiation is in between. The other thing to realize is that alpha radiation, it cannot get through our skin, so even our skin will stop alpha radiation, whereas gamma radiation can go through without any difficulty our skin and tissues. Right, so the next task was to sketch the symbol for the radiation hazard, and the symbol, we have a triangle, and we have the circle, which is meant to represent the radioactive isotope, and then we have the symbol that looks like this, and it's meant to represent the radiation moving out away from the radioactive source. Normally the background is yellow. Black on yellow is the normal symbol for radiation. Now, the next task, you had to choose from a list in a PowerPoint 3 safety rules that would be most relevant. Say which you think is the most important and why. So take a look at these on the PowerPoint. So these are the 5 typical rules that there would be for using radioactive sources. The first one is to never touch it directly, to use tongs or robotic arm. Second one, to never point a radioactive source at yourself or at someone else. Third one, to store the radioactive source in lead-lined containers when they're not being used. Fourth one is to wear radiation protection suits. And the fifth one to wear radiation badges. So your job is to choose which of the rules might be most applicable to use in school. So of those 5 rules, there's really only 3 in this case that would apply to schools, as generally in schools we don't have sources where we would need to wear radiation protection suits, and we don't need to have radiation badge monitoring equipment. The most important one is always never to handle radioactive sources directly. Always use gloves and tongs. Now, while it is dangerous, as we see in the second one, to point radioactive sources at someone so the radiation goes towards them, handling radioactive sources is the most dangerous thing to do, and that's because we must avoid, above all, contamination. And we will see in a later lesson that contamination where radioactive sources comes onto your skin is the most dangerous situation. So we need to avoid contamination by not handling the radioactive sources directly. Second rule, never point a radioactive source either at yourself or at another person. And the third one is to store radioactive sources in lead-lined containers when not in use. So now that we have finished this first set of lessons in the topic 4, the atomic model and radiation, you should make an attempt to answer the exam questions that are at the end of these lessons.